Hello, Blind Man Bird here, and in this demonstration I'm going to show you yet another way to explore what GeoGebra can do in terms of mathematical visualization. And here we're going to look at four common ways to define the center of a triangle. Actually, mathematically, there is no single center of a triangle, and in fact mathematicians have come up with hundreds of different definitions for the center. The most common, though, are the definitions that the ancient mathematicians have come up with. And those are the incenter, the circumcenter, the centroid, and the orthocenter. Once again, the point here called IC is the incenter. And in fact, the incenter is the central point of the circle which can be inscribed within a triangle. The circumcenter is the center of the circle which can be circumscribed around a triangle by drawing a circle using the 3 points of the triangle. The centroid comes from a definition which is a little bit harder to understand, and the orthocenter likewise has a very specific definition. So we're actually going to look at how to build this. I'm using the scroll wheel here to zoom in and out. And let me point out that this is being constructed using GeoGebra 5.0.125, although really any version of GeoGebra 5 for Mac or for Linux or Windows should work just fine. So this is actually a very advanced example because we're actually hiding a lot of stuff that's happening behind the scenes. If we look at the algebra window for this and we see the individual objects defined, we see we're only looking at a few things. We're looking at the points A, B, and C as inputs, and note that we can move them around. This is a dynamically changing diagram showing where the centers are as we move these things around. You'll notice that each time a point moves, the algebraic definitions for all these various points and segments and lines and circles is changing, and it can be changing quite fast, in fact. So there's some complex stuff happening behind the scenes. All three of these points, A, B, and C, can be independently varied. You can make them as small or as large as you want. You know, one thing I forgot to mention is you'll notice that there's a line between these 3 points: the circumcenter, the centroid, and the orthocenter. The incenter circle is not on that line. This is a line known as Euler's line, I believe. And it comes about from an observation that Euler did, which is that those three centers are always collinear no matter what. Now you can pick some really weird situations where actually certain things can become undefined. But as long as we keep the points A, B, and C distinct, this being A, this being B, and this being C, we can actually define just about any triangle and see how these things interrelate. So let's see how this was constructed. Another thing we can look up is the construction protocol, and that gives us an idea for how this thing was built. So we're going to actually follow the construction protocol to rebuild a new version of this very same file. And that will serve as it's going to be a fairly long, you can see there's a lot of things defined, but we're going to use that as a way of learning how to use GeoGebra. So I'm going to go ahead and create a new GeoGebra window. And because I want to see both the algebraic view, where did it go? Sometimes things come out behind, not this time. Oh, there it is, it just took a while. So basically, because I'm going to want to see both the algebra and the geometry, I want the algebraic view, and I'm not going to save this the changes we made to the file that we started with. Let's go ahead and start with the algebra view always opens with a coordinate axis. We're going to get rid of that coordinate axis later, but let's use it for now to define points. We're going to create 3 named points using the point tool. Okay. The first one we're going to put at, well, it doesn't really matter where, but let's say we don't want it constrained to be on the x-axis. We're going to actually set it a little bit high of the x-axis, and we're just going to put it here and call it A. Then we're going to put another point here, call it B. And then we're going to put another point here, and we're going to call it C. At this point, we really don't care about the axis. In fact, the axes are starting to bother me, so I'm going to get rid of them. We go under Options, Advanced. We go to the second pane, and you'll see right here there's a button that says Show Axes, so we can turn them off. Okay, so here's our points A, B, and C, and they're totally unconstrained. We can put them wherever we want. Constraints are a very important concept in GeoGebra. You can have either totally unconstrained inputs, and you can just move it about however you want. You can have partially constrained inputs. For example, I might be able to move A, but it's constrained to lie along a particular line, or within a certain shape, or along the perimeter of a circle, for example. And you may have totally constrained points that you can't move at all. And those will be those things that result from some kind of interaction between the unconstrained things, creating some kind of relationship that's fixed. Okay, so here's our 3 points. Next thing that would be useful is we'd really like to have a triangle defined between them. So we go to the Polygon tool, and we simply pick the 3 points, A, B, and C, and finally back to A to close the polygon. And there is our triangle. Now, we really don't want to see the name of the polygon, which is fine. That's the way it's set. We also don't want to see the names of these segments. So we simply turn off, we right-click on the segment group in the Algebra view, and we turn off Show Label. So that simplifies what we're looking at. Now, let's first work on defining the circumcenter. And you can go online to Wikipedia or to wolframalphamathworld.com and find out what the definition is. Oops, see what I'm doing right here is I'm clicking while I'm in this mode. Very dangerous. You want to try and return back to the arrow mode if you can, because it's safer. I wanted to move these things around, and instead I was starting to create a new polygon. Okay, so you can go on to Wikipedia, or you can go on to Wolfram's mathworld.com website, or any number of other websites to look up the definition of a circumcenter, which is what we're going to chart out first. But because of copyright reasons, I'm not going to display those sites. However, I will say that the circumcenter is described as the intersection of the 3 perpendicular bisectors of these lines going through the points. No, not going through the points, the perpendicular bisectors of each line. So in other words, we want to cut each of these lines in half, that means bisecting it, and then find the perpendicular lines that go to that. And fortunately, we have exactly that tool available right here where it says perpendicular bisector. That's kind of handy. So let's see, when we select this tool, it's been a while since I've used this, we have to give it select, oh, here's how we find out. Select 2 points or 1 segment. Well, that's perfect. We can either select A and B to bisect this, or we can just simply select this segment. Let's try just selecting the segment. Boom. There's our perpendicular bisector. Okay. Let's try it a little differently for the next one. Let's try, we select point B and point C. Boom. There's our perpendicular bisector. And finally, let's bisect this one just by selecting the segment again. Boom. Now, we didn't really need to draw all 3 of these. We could have just settled for 2. But what we're interested in is we're interested in the point, which is the intersection between these 3 things. So we go up to the point tool, and you'll see there's a sub tool within that called intersection. We position our mouse so that all 3 of these things are selected. Boom. We click on that, and we see there's a new point defined called D, which is actually the intersection of just D and, of 2 of the lines, but that's fine. It's going to work just the same. Let's go ahead and turn off, or actually let's go in and go into Object Properties. We want to rename this, because this is the circumcenter, to CC. And there's our first of the 3 things that we're interested in. We don't need to see any of these lines, so we can right-click. We're going to hide them now. So we're going to be kind of doing this again and again. We're going to be going behind, we're going to be going back over things that we've previously constructed and turning them off when they're no longer needed. So we don't need to see any of the perpendicular bisectors. However, we can't just delete them because this intersection is dependent on them. So we simply say, I don't want to see those things anymore. We right-click on line and we say turn show object off. Or if you prefer, you can individually turn them on and off here using these buttons. So now we've got our first of the 3 points. But the other thing I want to see is I want to see the circumcircle. I can define this either as here's the center of the circle and I pick any one of those points as the perimeter. But really, more conveniently, the circumcircle is defined by the circle going through 3 points, A, B, and C. So here's the circumcircle, and I want to right-click on it and not show its label. So there we've got the first kind of part of our system defined. We have 3 more to go. This is the circumcenter. It is the center of the circumcircle. Note that as we move these points around, this is a dynamic system, and GeoGebra will show you how these things move around, which is pretty darn cool if you ask me. Don't know how you feel about it. I think it's pretty cool. Next in line, and incidentally I'm reading from a script which is a printout, or rather a web page created. I'll show you how to do this at the end. We want to document what the construction protocol was. I'm just up to step 10 in my 30 some odd step sequence of how to make these things. Okay, so the very next thing we're going to find is the centroid of this triangle, which is sometimes called the median of the triangle. And I must confess that just now there was a skip in the recording because from the construction protocol I could not figure out how this was constructed. I had to go and actually look it up online just now, making a cut in the video. So that's occasionally happens. You just can't remember how something was constructed. That's perfectly fine. The centroid is defined as, if we take the medians or the midpoints of each of these line segments and then draw lines to each of the points opposite, the centroid will be at the intersection of those 3 things. Let's watch to see how that occurs. First thing we want to do is we want to bisect the lines. The way we do that is under this tool here, I think, or is it this tool? This tool here, we want to find the midpoint of 2 lines, 2 points. So we'll find the midpoint of A and B. That's not surprisingly this point here. Now we will find the midpoint between B and C. We just do it again. Click on B, then C. It creates a new point here. And finally, we want the midpoint between C and A. That's this point here. Now we construct lines, and we want these to be full lines. Actually, the centroid is always within the triangle. But just to be on the safe side, we want to create full lines, not just line segments, because sometimes points will lie on the outside. For example, the Incenter, I believe, can move outside the triangle. So let's join these up. Point A matches with point E. I'm now drawing lines using the line tool. Point B matches up with point F. Now really we can stop here because that's the intersection that we're interested in. And finally point C matches with point D. Let's now go to the intersection tool under the point tools here. And actually, because this is very close to that circumcenter, I'm just going to mess with the triangle so that I can get the circumcenter out of the way. Now I'm going to go back here to the intersection tool and simply get all 3 of them highlighted. It's only going to pick 2 in creating the intersection. Like if I double click on the definition of G, I see it happened to pick lines H, which is this one right here, and line I. It totally ignored line J. That doesn't matter. You want to have, that's just a detail of how GeoGebra works. Okay, now we don't need to see these 3 lines. Again, we're kind of cleaning up behind ourselves. So H and I and J disappear. And we also don't need to see F, nor E, nor D. Where's G? Oh, G is the centroid that we just created. So let's go right click on it and I'm just going to use the nomenclature CD for centroid. So that point CD is the centroid. Boom! We've done 2 of them. Okay, now the next thing we're going to construct is the orthocenter of the triangle. And in case you saw another jump, it's because I wanted to just double check with Wolf from mathworld.com and make sure I understood the definition of what the orthocenter is. The orthocenter is defined as the intersection between the altitudes of the triangle. What is an altitude? The altitude of this point C above this line is where a line draw from C that is perpendicular with this line segment match up. So if we take a perpendicular line from here passing through C, that's the altitude here. If we draw all 3 altitudes, or really we just need to have 2, then where they intersect, where those 3 things intersect, that is the orthocenter. So let's see how we construct that in GeoGebra. There is a tool simply called perpendicular line, and if you read the instruction about it, it'll say select point and perpendicular line. So we simply have to go in order, first picking, let's say, C. Now we have to pick a line that is perpendicular to. We pick this line down here, and there's our first altitude. Notice that wherever we move things, this line is always perpendicular to this line here is always perpendicular to the line AB, no matter what. Okay? So now we do the same thing. We pick the perpendicular line from A to line BC. That's going to be where the orthocenter is. And just for BOFs, we'll do the same thing with B being perpendicular to line AC here. They intersect. We do the same thing where we pick the intersect tool. Make sure all 3 are highlighted, although it's only going to pick 2. And then we go behind ourselves and turn things off. We don't need to see these 3 lines. KL on them. We also want to call point G OC to represent orthocenter. Okay. So now we're just one thing away from where we want to be. We also want to set up the Incenter. Oh, and incidentally, these are the 3 things. Let's do this now. These are the 3 points that you need to define Euler's line. You see that no matter where I go, these 3 points are collinear. So let's just go ahead and make a line, let's say between orthocenter and circumcenter. Doesn't really matter. Let's turn off the label of that line. So we're not hiding the line, we're just hiding the label. And that is Euler's line. Okay. The last thing we have to do is to draw the incenter. The incenter is defined as the center of the circle, which can always be inscribed within this. And I have to go back over my construction notes to figure out how I constructed it. Oh, it's done through bisectors of the angles. Yes. What you need to do is take each of these angles, like this angle right here, you need to cut it in half, and then where that line hits, and it's not necessarily going to be perpendicular, where that line hits the opposite side, you want that. You want to basically have the angle bisectors from each from each of these things drawn. So we want to bisect the angle. That is, let's see, I used to know how to do this. Angle bisector. There it is. Under this tool here where we have perpendicular lines, parallel lines, and so on, the 4th tool in, you'll see there's angle bisector. So here what we need to do is we need to select 3 points or 2 lines. In this case, 3 points is going to be easier. We can, well, actually, let's do it both ways. By selecting, let's say, angle BAC, by selecting these 3 points, BAC, that is the angle bisector here. We'll see that no matter where we move our points, that's always cutting that angle in half. It's kind of not always obvious, but it is. Okay, let's go back to angle bisector. Let's do it a little differently this way. Let's say to bisect this angle going through C, we're going to pick this line segment I should say, and this line. Boom! Now that's interesting. It drew two lines there, so that's a little bit odd. I don't think I trust that. I'm going to undo that, and I'm going to go back to the way that I know works. That might have been a bug that we just saw. So we're going to make an angle here, A, C, and B, and that's the second angle bisector. And we notice that it's kind of close to this line, so I'm going to mess it up so that the incenter is not anywhere close. Yeah, the incenter is going to be down here. So now we bisected, let's see, we bisected this angle, the angle passing through C, the angle passing through A. Now we just have to do the same thing for the angle passing through B. So we simply say angle bisector, C, B, A, and there's our third bisector. Where these three things touch, that is the intersection point, which is the incenter. So we go back, we use the intersect tool, we click here, we do a little cleanup where we don't need to see these three lines, but we want to keep the line N, which is Euler's line, and we want to keep the circle here, which is the circumcircle. So point G is going to be renamed to IC for incenter. And finally, to finish our diagram, we want to actually show this circle here. So we note that one of the things that's kind of interesting about the incenter is that it's the circumcenter and the orthocenter that can leave the triangle. The incenter and the centroid are always on the inside. That's right, I forgot about that. But what we want to do is we want to finally draw the inscribed circle. Well, one way to do that is to simply take the regular circle tool. You could, the more complicated way to do this would be to take, find the perpendicular. Let's do it this way first. Yeah, let's do it the more complicated way, and then I'm going to undo it and show you the simple way. Just because it's more fun to play with this. If we take perpendicular line and we simply say point, line, point, line, point, line, we see right here we have a point, and a point, which is where that circle passes through. So the last thing we have to do is we have to have anchor points here by using the intersect tool for here, here, and here. Oops. Those are our anchor points for the circle. We now go up here to the circle tool. We say circle through 3 points. This point, and that point. And that creates our inscribed circle. But you know what? There's an easier way to do it. Oh no, there isn't an easier way to do it, I just realized. That's the way to do it. For some odd reason, I thought you could just draw a circle by going from here to this line, but you really can't. You have to have a point there. So you have to have, you could simply, the way we did it, we defined the 3 perpendicular points here and then figured out the circle. A simpler way to do it would be just to do one of those 3 and then just to find the circle centered here going to there. But I kind of like the way we did it. That's actually more like if we had a, if we were using like a compass and a straight edge, that might be the way to do it. Here, once again, we want to do a little cleanup. So we want to turn off S and T, and for some reason this got called A1. We also want to turn off the points G and H and I. And we want to rename, we also want to turn off the label for this guy here. Or if we wanted to, we could make the label of this circle, the inner one, we could rename it to be IC for incircle, right? And then we could rename this this circle here G, the outer one, to be CC for circumcircle. Now I know I went through that very fast, but at this point we're done. We're quite done. And if we move these points around, we can see we've got what we started with. We have a nice little representation where you can change the triangle to be whatever you want. Oh, I hit the scroll wheel by mistake. And this will move around. Now when you actually are working with this, you're probably going to want to turn off the algebra window, because that's a lot of information you don't need. This right here is really wonderful in that it presents kind of a graphic view of what's going on. When you change the definition of the triangle, you can really actively see where those four centers move. And that's the beauty of GeoGebra. It's going to actually show you the geometric relationships, and you can kind of hide all the algebraic complexity that is occurring here when you actually represent the equations for each of these points, circles, and lines in terms of algebraic definitions. Now I will say that one really cool thing you can do is you can also open up the construction protocol. Think of the construction protocol, and I need to make it bigger. Think of the construction protocol as being the recipe we followed to create this. So if somebody wanted to recreate this beautiful diagram that we did, they would just simply run through the 32 steps that we did. You define the 3 points. You then define a triangle here, which is 4 separate steps in one. Then we defined the perpendicular bisectors. We arrived at the circumcenter. That also enables us to draw the circle. Then we define the points, which are the midpoints of the lines, and the lines that go through those midpoints to the opposite points. And when we find the intersection points of that, we have the centroid. Then we look at the lines which are perpendicular to each side, and that brings us to the orthocenter. Okay. Then we find the angle bisectors of each of the 3 angles. We find the intersection of those, and I'm having trouble reading this, but intersection point of, yeah, I'd have to go through it to really figure this out. But you put all those things together, and the incenter, oh, here it is. The incenter is the intersection of those things. Finally, we have somewhere defined in here, we have the line, which is Euler's line, and also the circumcircle. That's this last thing here. I'm sorry, not the circumcircle. The incircle was the last thing we defined. Oh, these things, I remember. These things were how we had to define those perpendiculars to enable the drawing of the circumcircle. So here's where we found the incenter point. That's step 25. And then steps 26 through 31 are all of the things that we needed to do to reach to be able to pick the 3 points associated with the incircle. And we can see that, like the algebraic view, as we move these things around, the definitions are not changing, but the values for these things are changing, which is pretty cool. So you can have a very fun kind of interactive demonstration with numbers flying about quite a bit. But to me, really the thing that says it all is if you turn off the algebra, you turn off the construction protocol, and you just make it a very simple window, you have a very powerful tool for describing some very complicated mathematical relationships, including Euler's line, which is kind of a cool concept. Now here there's a bug. I don't know why it doesn't let me pick up these points. There we go. You notice that when I was in the arrow tool, after I turned off those windows, I couldn't move any of the points. That's a bug that I need to report. So there are a few little bizarre bugs like that, but oftentimes if you just simply reselect the tool, or worst case, quit GeoGebra and just open it again, you'll clear out whatever kind of weird state that you're in. It's not a perfect program, but it comes pretty close. All right, so I hope you enjoyed this definition. The last thing I'm going to leave you with is a recommendation to watch a film by a friend, film by, hold on a second. If you go to this Vimeo page, created by a good friend of mine, Eric Cornwell, you'll see the 1950s and 1960s mathematical and science visualization films of his parents, Bruce and Catherine Cornwell. And there's some really remarkable stuff in here. And in here, I forget exactly where it is. I found it before. Oh, if you go to next, you will find journey to the center of a triangle. And I can't play that here. Here he goes. Journey to the center of a triangle here. And because it's copyrighted, I can't actually play this. But I'll provide you the link, or you can look right here. It's vimeo.com channels BKC Films page :2. And that will take you to this video here, Journey to the Center of a Triangle. There are no words used in this math demonstration, which I think is wonderful, and purely graphic imagery to find the same exact 4 points that we did. So it's really a wonderful demonstration film to reinforce exactly what we just went through. Okay, I hope you enjoyed this math talk, and I'll see you soon.